This is number 8 from Unit 2 of the workbook. When a student mixes 50 milliliters of 1 mole per liter hydrochloric acid and 50 milliliters of sodium hydroxide in a coffee cup calorimeter, the temperature of the resultant solution rises from 21.0 degrees Celsius to 27.5 degrees Celsius. So first of all, there is a typo in that sentence. We either need the concentration of the sodium hydroxide or that reagent is in excess. So we're going to go back and we're going to adjust that concentration to 1 mole per liter. Then we're told to calculate the enthalpy change for the reaction, assuming the calorimeter loses only a negligible amount of heat, that the total volume of the solution is 100.0 milliliters, the sum of the two individual volumes, that its density is 1 gram per milliliter, and the specific heat capacity is the same as for water, 4.184 joules per gram per Kelvin. So I'm going to write out the equation: hydrochloric acid plus sodium hydroxide will produce NaCl and water. And the whole reaction is 1 to 1. I'm going to fill in the given information that I have 50.0 milliliters of a 1.0 molar solution for both. And again, it was a typo that concentration was left out. So the first thing is, whenever we do a calorimetry problem, we have to realize that there are 3 steps. We need to figure out what happens to the solution, Q of the solution, how much energy is gained or lost by the solution. We know that that's equal and opposite to Q of the reaction itself. If the solution warms up, it's because the energy was lost by the reaction, and vice versa. So Q of reaction is negative Q of solution, and then we can work out to delta H. Delta H is equal to Q divided by number of moles. And that number of moles can be found from a mass or from a concentration and volume, depending on what you're given in your question. So we have first Q of solution. So we get it from the temperature change and the heat capacity, so mc delta T. Our delta T we can get from the information in the equation. We know that it's the final temperature minus the initial. The final temperature was 27.5 degrees Celsius. And the initial temperature was 21.0 degrees Celsius. So our delta T here is going to be 6.5 degrees Celsius or 6.5 Kelvin, because temperature changes in degrees Celsius and Kelvin are the same. We also need to know the mass of the solution. So we can get that from the density times the volume. The density, we're told in the question, is 1.0 grams per milliliter. And we're told the volumes are additive and that the two solutions add up to give me 100.0 milliliters. So 100 to 2 sig figs, actually, 100 grams, but the 2 sig figs is only going to be the same as my temperature into this equation here. 4.184, same as the specific heat capacity of water, 4.184 joules per gram Kelvin, and times delta T. So our Q ends up being 2.7 kilojoules. But we keep the exact unrounded value in the calculator. The next step, Q for the reaction, its negative Q of solution. So although this quantity was positive, Q for the reaction itself will be negative 2.7 kilojoules. Then we have to do delta H. Delta H is equal to Q divided by N. The number of moles here would be of the limiting reactant if there's more than one reactant, but if we look at the concentration and volume of both reactants, we see that the concentrations and volumes are the same, the number of moles are the same, and the stoichiometric coefficients are the same. We have stoichiometrically equal amounts of the two substances, so it doesn't matter which one I take. It'll come out the same either way. So I'm going to work out number of moles from HCl. It's C times V, concentration times volume, or sometimes people say molarity times volume, because this concentration is in units of molarity, moles per liter. So we have 1.0 moles per liter times a volume of 50.0 milliliters. If we change our units to liters, we should get 0.050 mole. So that is the number of moles. It would be the same for sodium hydroxide, and that's the number of moles I need down here. The Q, of course, is always Q of reaction. That's why we worked it out. Divided by the number of moles, and we get negative 54 kilojoules. So we kept the unrounded value in the calculator, divided by 0.05, and to 2 sig figs we get negative 54 kilojoules of energy for this reaction.